Hello, everyone. Thanks for coming out tonight. I'm excited to introduce our speaker, Professor Jamie Bock. For those of you who regularly attend our talks, you might have noticed we are not in our usual location, and that happens to be because Professor Bock is part of Caltech's Department of Astronomy as a professor of physics. I wanted to make sure I get the order right there. He is also a senior research scientist at JPL. Professor Bock has been at Caltech and JPL since he started as a visiting faculty member and postdoc. While he's been here, he's given us a window into the past through a wide number of observatories. Then these include observatories that have been ground-based, space-based, balloon-based, and I think there are even a few sounding rockets in there, so just a ton of different things. One of his more recent endeavors is SPHEREx, which will image the entire sky 4 times in near infrared and over its planned 2-year lifetime. So, here to tell us about this window into the early universe is Professor Jamie Bock.
Okay, thank you for the kind introduction. I also wanted to thank Michelle. When we were having our site visit with the artist who made that display on whiteboards, that was at the Keck Center, and so we sort of turned it upside down for several weeks, but it had a positive impact in the end on our project. So SPHEREx, this logo is meant to illustrate the science it does and also capture the fact that we map the entire sky, aka the celestial sphere, which goes with the name. And we've just been selected, February, for NASA's next medium class explorer mission, or MIDEX. We've been in development, starting with some crazy ideas, as Michelle says, for more than 6 years, writing many pages of proposals and enduring many all-day site visits. And now that we're selected, we're getting to the point where we can start to build it. And the building phase actually goes pretty quick. Our launch, if all holds together, is going to be at the end of 2023. So not a long time in the space business. Okay, so SPHEREx, as I'll describe, does, I think, some very exciting science. In the process, we map the whole sky, and it has a very attractive and elegantly simple implementation in order to do all this. Okay, I just wanted to say thank you to the science team who, their determination made all this possible. And you can also see it's about 30 people. It's not a huge team. It's a moderately sized project. And I wanted to particularly thank the 2 members of the science team who are on the project team, and that is Phil Korngut, the instrument scientist, and Olivier Doré, the project scientist. Okay, so what is a MIDEX? So these are missions that are competed in NASA. NASA defines basically a multi-parameter box, cost, volume, mass, that you have to fit into, cost usually being the driving one. And there are different size boxes that come with it. We are the medium box, but there is no bigger box in astrophysics. $250 million, get a free launch with that. And a smaller version is called a SPHEREx, or Small Explorer, and it's less money and a smaller vehicle. So originally we tried as a SPHEREx and we didn't get selected. Then we went double or nothing, basically, as a MIDEX and to get selected. So here are some recent MIDEX and SPHERExes over all of Explorer, well, all of time in these competed missions for explorers. And you can see they come in 2 flavors, astrophysics and heliophysics. And typically in astrophysics, we're talking about 2 of these per decade. So not that frequent, but they do come on a regular cadence. And then these launch, these costs gradually creep up with time with inflation. So roughly the same size thing. You might, if you're in astrophysics, you might recognize some of these missions, including a mission called WISE, which was an infrared all-sky survey and imaging, and we're following that up doing spectroscopy. Okay, so when we started this whole process, we knew it would be a a long road, so we humbly asked ourselves, what are the most important questions we could answer in astrophysics? And okay, we're not going to answer these questions completely. We're going to pick some targeted part of it and home in on that. But we're addressing how did the universe begin, how did galaxies begin, and what were the conditions for life to begin? Not on our solar system, but in general, in the universe. So I think those are pretty compelling questions. And you will see that we do these kinds of investigations in very targeted ways. Now, we're not the only ones who think this is important. They're actually written in the NASA science plan for astrophysics. We didn't really plan this, but then we happily noticed that our themes actually lined up really well. And so we made a big deal out of it. Okay, but first, let me describe how it works, and then we'll come back to the science. So this is basically SPHEREx in a nutshell. It's a little telescope, 20 centimeter effective diameter telescope. It's all cooled because we're observing at infrared wavelengths. So what we don't want to see our telescope glow. We don't want to see photons from our telescope. We have to have the detectors cooled. So there's a cooling system here, and I'll explain how that works in a bit. And it's not a very big thing. It's about as tall as I am, 2 meters, and it's not as wide. It's wider than I am, thankfully, about 1 meter in diameter. And here is how we fit in the launch vehicle. I mean, it's pretty ridiculous, right? We're this tiny little thing. There's room for more, but these are the vehicles we were given, so we happily fit in there. And the general resources we're talking here are pretty modest, about 200 kilograms. Data rate, 135 gigabits per day, not that stressful, which is important if you actually want to fly this mission, because as a colleague of mine says, the best science mission is the mission that flies. So that has always been our objective, is to fly. And then a couple of things about here on the wavelengths. Here's the spectral resolving power. So it's kind of like 100, which means we can see about a 1% variation in the wavelength. Not extremely high spectral resolution, and it varies with the band, as I'll describe. And then the spatial resolution, again, is about 6 arc seconds. In astronomy, that's pretty coarse, but we need that in order to cover the whole sky. Okay, so the first trick here is the telescope. Why is this thing powerful? Well, we want to map the whole sky. So we want a lot of ability to collect photons. And it's important to note that that ability is the area of the telescope. We're all aware of that. Bigger telescopes are more powerful. But it is also times the field of view of the telescope. And it's really the product of those two things. So SPHEREx, with its small mirror here in green, is not even half the size of WISE. It has 1/4 of the collecting area. But the field of view is enormous. And so we have 65 times more field of view on the sky than WISE does. And really, it's the product of those two things. So even though this telescope is small, don't let its size deceive you. It has enormous photon collecting power. And that factor of 16 is a big deal, allows us to do these demanding measurements. You can see it's got 3 mirrors. This is an interesting design. It's actually all off-axis, and it's obviously all reflective with the 3 mirrors. To make the maximum use of the field of view of the telescope, we actually go one step further, which is we split the beam into 2 colors. So there's a color that's in transmission and a color in reflection, so we kind of double our money, get twice the field of view that way. And in total, we have about 25 million pixels in the focal plane. So that's the first trick. Small telescope, but big collecting throughput. The second trick is how we do spectroscopy. And astronomers are used to saying, I want to get the spectrum of that object. And so let's put all of my observing power onto that one object. Well, our optimization is different. We want to map the whole sky. And therein, eventually, years in conception, we finally figured out a good way to do that. Okay, so basically what we do is we take a filter. It's a allows certain wavelengths to pass through, and the wavelength that passes through the filter varies as I move along the filter. Okay, so as I go from this side, it's transmitting at red wavelengths as an optical filter, and as I go here, it's transmitting in the blue. And this technology, you can see it here in the optical, but it works great out in our wavelengths and the near infrared, longer wavelengths. So we designed one of these things, and Phil here tested it, and this shows the wavelength progression. And now this is the design, and you can see the wavelengths progressing from just at the long end of optical out into the infrared. And this is what we measured. So works really well. Very efficient, did exactly what we wanted. And so we built a test focal plane, as one does, to show that we have all these technologies under control. So this puts 3 of them. That's half of our area. Here's Phil with the assembly. And this goes into one focal plane. And then ultimately, there are 2 of these guys. OK. And what this filtering technology does is, in order to make an observation, we want to take a source and place it at 96 different places to get 96 different measurements of its spectrum. In fact, because of this splitting business, we only need 48. And you can see here as we march out, each image captures a different wavelength. What that means is, the object I'm interested in, perhaps, is only being observed once, but everywhere else on the field of view is observing some other place on the sky. So we can stitch all that together, and then we get a complete spectrum of everything. So basically, we need to take this series of pictures, 48, and we get a complete spectrum. And we get that over the whole sky every 6 months. So every object gets a complete spectrum every 6 months. And we have a 2-year mission, so we get 4 complete spectra at least of everything. Belatedly, we found that this great idea was not a new idea. It's been used in planetary, well, new to astrophysics, it's been used in planetary science for quite a while. Well, that meant it's a good idea, right? And in particular, this mission that went out to Pluto, New Horizons, used almost exactly the same approach with a filter placed over their detector to make rapid images of things like Pluto and Jupiter. So it works well. All right, so then the next thing is where do we put SPHEREx? What orbit do we choose? So here's the Earth, and you can see this is the dark side of the Earth. And here's SPHEREx, much blown up. It's kind of like the size of England or something in this picture. OK, so our orbit goes like this. We're always going around the sunrise-sunset line around the Earth. And the Earth goes around the sun. We're always going around that line. So eventually, we're always looking at 90 degrees from the sun. Eventually, over 6 months, we spin all the way around and we map the full sky. So there's SPHEREx again. And because it's cooled, we have to avoid seeing the sun. And actually, we have to avoid seeing the Earth as well. Because the Earth is sitting down there below us. It's blasting infrared thermal emission. And so we have to shield against that. So what that means is we always have to point the spacecraft at least 91 degrees away from the sun. So we never have it shining into our optics. And we have to stay within 35 degrees of the local zenith of the Earth. The way we cool the system is we actually use something that's basically free in space. I love things that are free. And what we're using is just the fact that space is cold. And so we can radiate away our heat to space with using things that are like pieces of metal made shiny or black, phased appropriately. And this is not a new idea. This is a satellite I worked on called Planck. And it went out to a place called L2, which is well away from the Earth. And so it simply radiates out the heat to outer space, which is very cold. And it does that in multiple stages. So you can see 1, 2, 3. These things are called V-groove radiators. And then the 4th stage is really the telescope. And it cools that telescope to 36 degrees above absolute zero, which is pretty impressive. It keeps going. There's more coolers in this system that go all the way down to 1/10 of a degree above absolute zero. But we don't need that. For SPHEREx, we basically have the same approach. You see these guys down here. These are the same V-groove radiators. But we are always going around the Earth. We always have the sun off to the side. So we have to shield them. So we have these things lovingly called photon shields, which protect the cold telescope in our detectors from seeing that radiation from the Earth and sun. But it's free, as I said. There's nothing that determines the lifetime. SPHEREx will just continue to stay cold as long as it stays up in orbit. We do the same trick here where we use the telescope and another panel as additional cooling stages, and ultimately we get the telescope to 42 degrees, and the longest wavelength detectors want to be a bit colder, so they will get down to 38 Kelvin. Now these are our predicted numbers. Our requirements are not as demanding. All right, so now let's put it all together and see how we observe the sky. Okay, so here's SPHEREx. This yellow arrow is where the spacecraft is pointing. These are the LVFs, the focal planes imaging the sky. So we take a picture. Actually, that picture takes about 150 seconds, and it takes us 95 minutes to go around the Earth. So this is much sped up. And so we just keep doing that. We move it a little bit so we get a different wavelength every picture. And then eventually, as we're going around the Earth gets in our way. So we do a big slew to point, again, well away from the Earth. And then we continue this process. We take a couple of pictures and keep doing that until, again, the Earth gets in the way. Then we do another big slew. So basically, what's happening here is the spacecraft is pointing our camera where we want to observe. And we just have this automated sequence of exposures that collects all the data. And you can see the observations here or here on the inset are kind of sparse. It takes many days or weeks even to get a complete spectrum of anything. But this just builds up over time. And again, after 6 months, we get the whole sky. All right, and here's how it builds up. So here's the observations. This is at one wavelength. Blue means we've observed it once, region of sky. And this is the coverage we'd have at a month. You know, some places here we've missed, some places we've hit twice. I should say the simulation isn't perfect. It's getting better all the time, but still not perfect. Here's what it looks like after 2 months. We've covered more sky. Basically, we're observing here in what astronomers call a great circle. We're just looking opposite the sun, you know, taking pictures along that line. So that line forms a circle on the sky, and what you're seeing is that rotating as the Earth goes around the sun. And here we are at 7 months. So at 7 months, we've completed the full sky, and we've done a little more here. We've actually got 2 hits in this area. You'll notice this is kind of noisy, but the orbits also cross always at the poles. And so we have deep observations that happen at the poles because we cross those every orbit. Here we are at 13 months. Again, it looks like 7 months. You can see we're getting 3 observations here. And then at the end of 25 months, which is our stated mission life, we've covered the whole sky 4 times. Okay, so that's basically how SPHEREx works. Hope I explained that. It's fairly, I think, actually fairly simple for a space mission. Now let's go back to our science questions, and let's start with the first one. How did the universe begin? And I'm going to have to take you back briefly through the history of cosmology, just quickly though. So let's look at what we thought about cosmology in the 80s. So we knew the universe is expanding. And that's because Edwin Hubble up on Mount Wilson showed that galaxies are receding away from us at a rate that increases the further they're from us, which could be explained as the whole fabric of space basically expanding everywhere. That was well established. It was a big surprise at the time. If you take this and work backwards, you can say, well, what was the state of the universe like at earlier times? Well, obviously it's getting smaller, but it's also getting hotter. And so these folks predicted that there was a period when the universe was very hot, hot like the inside of the sun, and that should leave a remnant glow that we could maybe observe today. And in fact, in the 60s, these guys out in New Jersey discovered the cosmic microwave background, this residual glow from the early universe. And so this established what's called the hot Big Bang. It means the universe had a beginning and it was hot. So we go back in time, the universe gets hotter. This glow from the microwave background comes to us from a time when the universe has gone from being ionized, in other words, free electrons and free protons, to neutral, forming basically hydrogen. That transition happens when the universe is about 3,000 degrees, which is like the temperature of the surface of a cool star. Our star is somewhat hotter. And it's been stretched by a factor of 1,000. The universe has expanded 1,000-fold since that time. And so its temperature has gotten cold. And so this characteristic temperature, the glow, is like 3 Kelvin, a factor of 1,000 smaller, because the wavelengths have been stretched by the expansion of space. And there were still some doubters, but in the 90s, the predicted spectrum of the microwave background, it has a characteristic spectrum that was predicted by Max Planck around the turn of the 19th to 20th century. And these error bars are times 500, so it's exactly a Planck spectrum. And this is really a triumph of what the hot Big Bang paradigm. It's really hard to explain this any other way than it being a remnant glow from the early universe. Okay, fantastic. Now, here's what the microwave background looks like. And just to get you oriented, this is a picture of the whole sky. So it's like, a two-dimensional image of the surface of the Earth. It's a sphere, except we're looking up. This is what it would look like. The sky, well, would look like, is what it does look like. These are images taken a bit longer than optical wavelengths over the whole sky. You can see the plane of the galaxy. You can see some dwarf galaxies that orbit our galaxy. So now let's say, what does this picture look like at millimeter wavelengths? And this is what the picture looks like. This is actually real data, by the way. If you have sharp eyes and a projector with the right color stretch, you can see some features, but you'll have to look really hard. The microwave background is all sitting here at one temperature. And that's a problem. So cosmologists in the 80s were really befuddled about how that could possibly be. And the reason they're befuddled is you ask yourself, how far does a photon get from the Big Bang to the time that the universe becomes neutral? So it's about 400,000 years. Well, the answer is about 400,000 light years. And that patch, according to Einstein's theory, is the furthest information can travel. Okay, so now today, we're looking at the whole sky. How big is that patch? Well, it's about the size of my laser pointer on this screen. In fact, if I look on this direction, I see photons that have just gotten to me. And I look at this direction, that photon has just gotten to me. There's been no way for these two patches of sky to communicate. And yet they're at the same temperature. They're at the same temperature to like 10 parts per million, all right? So what's going on? So the solution to this is very much not obvious. And it emerged in the 80s. It's a theory called inflation. And I love this graph because it's got 50 orders of magnitude on the x-axis. And it's got 100 orders of magnitude on the y-axis. All right? Everything we know about the universe, the furthest we can see back to that neutral period from the cosmic microwave background, the last time those photons interacted with matter, that's between here and here. Okay? This is all we can see. All right, but the idea is, how can we solve this conundrum? And the theory basically is the universe went through some violent expansion in its early times. Basically, the observable universe was happily all connected to this early times. It was all in thermal equilibrium. It's all communicating happily. And then something happened. Space rapidly expanded. And rapidly expanded so fast that two observers sitting next to each other were basically thrown outside their causal horizon. They remembered the temperature they had, but they're no longer in communication. So the entire observable universe basically got flung apart. If you like, you could say space expanded faster than the speed of light, which is consistent with Einstein because we're not actually transmitting information. Okay, cool. And so how do you get this to happen? Well, it turns out, Einstein says the universe follows these certain laws, and it follows the laws according to what it's made out of, how much matter and energy. And if you have a really weird form of matter energy, say something with a negative pressure, you can get this exponential type of expansion. Okay. Well, there's a couple of other things to notice about this phenomena. Of course, this expansion somehow magically turned off, and the universe proceeded on its merry way. Now, you remember the universe gets hotter as we look back in time. It gets smaller. Well, from here to here, it shrunk by a factor of 1,000, and it got hotter by a factor of 1,000. If we extrapolate back, well, this is really hot or at really high energies. So what kind of physical process would cause this expansion? What would cause that? Well, the honest answer is we don't know. Of course, scientists hate to say that. So we model it phenomenologically. And the reason is that these energies here associated with inflation really just go beyond what we know about particle physics at the highest energies. That doesn't get us down to here. So this is a physical process that happens at such high energies. Maybe it has something to do with the unification of forces in nature. The other thing to notice about this graph is here the observable universe is quite small. And what inflation does is it takes initial fluctuations. This is really the quantum scale here. So there's naturally occurring randomness in nature at that scale. And inflation basically blows that up to enormous sizes. And so that's pretty profound. The largest things we can see in the universe are really sourced by the smallest things we can see in the universe. Galaxies and clusters of galaxies really began their life as minute quantum fluctuations expanded to enormous scales. It also means that this is the radius of the observable universe, but very likely the universe at this early time was bigger, and so you might ask, how big is the real universe? And we don't know because we can't see it. It's outside of the furthest we can see in light, but it might be something like 10 to the 60 times bigger than the enormous universe we can observe, which is also pretty profound. Okay, so time marches on. Now we're today. This is the latest, greatest map of the microwave background. Now I've taken out a constant signal, that orange constant signal, just subtracted that mathematically. Also subtracted the fact that we're moving with respect to that, which produces a dipole, and artfully removed the plane of the galaxy, which we would see here. And this is our best measurements of what's going on in the universe. And what we find is that all the predictions of inflation have basically come to pass. One of the ones that's most easy to understand is that there's a characteristic scale here which has to do with the speed of sound in the plasma. It's a pretty clean measure. And the end result is that the universe has a geometry that's basically consistent with being flat. Flat geometrically in the sense of Euclidean geometry to better than 1%, as good as we can measure. And you can understand that. If I take any shape with inflation and expand it enormously, it's going to look pretty flat. The Earth looks very flat locally. Okay, there's a bunch of other things here. My laser pointer, as I said, is about the size of that patch that's in causal connection. But you can see structures that are much bigger. And that's basically the idea that something set that up, something that doesn't have to do with causal physics, something like inflation. These fluctuations also go on to seed structure, and one can study their spectrum and their phase, and this is all consistent. And this sounds nerdy, but there's a reason I'm saying this. The fluctuations have Gaussian statistics. So that means like if you look at the distribution of fluctuations, they follow a characteristic distribution called a Gaussian distribution, as well as we can measure. Okay, so this inflation stuff really seems to work. All right, so let's do our first question. What's SPHEREx going to contribute to this puzzle? How did the universe begin? So this is now summarizing what we know about cosmology. Here's this early period of inflation, moments after the Big Bang. About 400,000 years later, this is the last surface that we see with the cosmic microwave background. From this point on, those photons basically stream to us. These little hot spots and cold spots, minute temperature variations in the background, those fluctuations were set up by inflation, and they don't stop there. There are overdensities and underdensities, and galaxies then fall into those overdensities. And so we can map that out. This webby structure you see here is a depiction of that process happening. It's called large-scale structure. Basically, those fluctuations attract matter, mostly dark matter, that initially fall into the slight overdensities, and that process just continues and continues. And then eventually galaxies land in those overdensities and light up and turn into stars that we measure. So there's another way to probe cosmology, and that is to look at this large-scale distribution of galaxies. And because these little fluctuations in the microwave background are sourced by inflation, inflation also influences the structure that we map out with this large-scale distribution of galaxies. So in particular, we want to study the statistics of the fluctuations that started from inflation to see if they continue to be Gaussian. All right, so why is that? Well, if we want to understand this physical process of inflation, and as I said, we don't really know what happened, and really our best empirical evidence is probably going to come from the universe itself, at least for the foreseeable future. So what can we do, given that would improve our understanding? Well, there's really two kinds of measurements these days. One is that inflation blew up quantum fluctuations, but there may have been a quantum fluctuation basically associated with fluctuations in space-time. And those those are basically gravitational waves. So depending how inflation occurred, that might be detectable. And it's best done in the microwave background, which until recently was my day job. The other way to probe it is this distribution of fluctuations, this property called non-Gaussianity. And it's sensitive to whether inflation has one field that drives it or more. Okay, so the basic idea here is you can use the CMB to study non-Gaussianity, but the limits are now just limited by cosmological noise. And that's because the microwave background, as we see it, is basically a 2D surface. But these galaxies are really a 3D thing. We get a distance for all those galaxies. So there's more information there. And so it turns out that large-scale structure is more powerful. And here's a depiction of large-scale structure, cartoon. And I've changed the amount of non-Gaussianity here by a lot, way more than we intend to, much bigger than our errors. And so what you see here is this orange stuff is largely dark matter. It's fallen into those overdensities. And galaxies then fall into that dark matter and they turn on. So these blue things are galaxies. Obviously, we can't see the dark matter, but we can see the galaxies. And so they're basically the snow on top of these mountains of dark matter. And we can see the snow, and we can use that to trace out the underlying dark matter and the underlying fluctuations. If I turn on or off this level of non-Gaussianity, it changes kind of the overall amplitude. And so this happens on very large spatial scales. So then the idea is I can quantify how clustered galaxies are by seeing how they vary as a function of position. They cluster together because they're all associated with this underlying dark matter. And I can do that in a 2-point way or a 3-point way, make triangles or lines. Okay, so this is basically what SPHEREx does. And in order to do this, we need to cover a large volume survey or, the whole sky. Okay, so this is a graphical depiction of basically doing that. Each of these galaxies is predicted to be in the SPHEREx data set. Basically what we're doing is we're determining through spectroscopy the distance of each of these galaxies. And so we make this map of all the galaxies. And this little visualization here, we're flying through it. Now, the light blue stuff, that's dark matter. And then the galaxies are basically tracing out that dark matter. And you can see also as we go further and further out, this is a redshift. So we're getting further and further away from today, going back in time. You can see there's fewer of these galaxies as time goes on. And that's because they get harder and harder to detect. Okay, so I'm going to skip the next two graphs because they're kind of technical. But this is the basic idea. We measure the distribution of galaxies in 3 dimensions. And then we study that structure. And we can work backwards and talk about the initial fluctuations set up by inflation. Okay, these are the ones I'm going to skip. At Michelle's suggestion. Okay, let's look at our second science theme, and that's how did galaxies begin? Now, so this is basically the same cone you see here, history of the universe expanding. But now we've painted the evolution of galaxies on it. And we know the evolution of galaxies in broad brushes. Some point after the microwave background, the universe was just consisted of neutral hydrogen. That slowly, it's called the Dark Ages. Nothing much happened. Hydrogen gradually coalesced, and at some point, the first stars turned on. And so that's these points. And as those stars turned on, they're emitting ultraviolet light, and they start to ionize the neutral gas that surrounds them. And we know, looking back to about 500 million years, we've completely ionized all the gas in the universe. So this process is called the epoch of reionization, and it's not well studied. We don't really know the process when the first stars turned on, although we know it must have happened. We have some rough constraints. Galaxy evolution continued, and there's a peak of star formation that happened about 5 billion years ago. Sorry, 5 billion years after the Big Bang. It's called cosmic noon. It's basically when star formation in galaxies was most vigorous. And I'm sorry to say, it's been on a slow decline ever since. Today, the rate of star formation in galaxies is lower. So the usual way to study this process is to study the individual galaxies. But there's another way one can study them, and that's to look at something called the extragalactic background light. It's just the total glow produced over all cosmic time by photons from these galaxies. It's kind of like the microwave background, except now we're observing the light from these galaxies. And it's just a glow on the sky, and it's kind of like the total of all this emission. It all just piles up, and it encodes everything that happened in cosmic history, all the light produced by these first stars through cosmic noon to the present day. Okay, but there's a problem. We can't just measure the total glow, and that's because there's stuff in the way that's much brighter. In particular, I think you can see there's the galaxy here, but there's another source of emission, this stuff. Anyone know what that is, by the way? G knows. Yeah, it's something called zodiacal light. So it's the fact that our solar system is in a dust cloud, and that dust at optical wavelengths scatters sunlight. So this picture was taken just after sunset. So this kind of triangle business here is sunlight that's scattered off of that dust that's mostly in the plane of the planets in our solar system. If you go to longer wavelengths, you see this stuff emit thermally. It's about the same temperature as the Earth from where we're observing it, at least. And it's really bright. So people have tried this. I've tried this. And it's pretty difficult. So, but there's a trick. These backgrounds, or I'm sorry, foregrounds, are very spatially smooth. So the trick is look for structure from the extragalactic background. And we're using the same idea that we have with inflation. There's an underlying dark matter. The galaxies trace that out because they light up where the dark matter's the densest. And we can use the fact that it traces it out as a tool to measure the total background light. And it turns out that these foregrounds, particularly the zodiacal light, is very smooth, and we're always moving around in it. So it changes, and we can use that as well. That's the idea, is to not, well, I'll illustrate it. Okay, so here's some data that was taken at longer wavelengths by a project called Herschel. So this is about 100 times longer wavelengths. But the cool thing about this image is really big. This is the picture of the moon. And I think you can see just by eye, you can see this clustering structure that's in the image itself. Most of these objects, you can't actually determine if it's a 1 galaxy or 2 galaxy or 5 galaxies. But this large-scale fluctuating structure comes out really cleanly. So the method really works. The problem is that all these photons, if you just do it in an image, you're piling up all the photons over cosmic history. So there's some uncertainty as how you break that apart in time. In the near-infrared, in the optical, there have been a number of measurements done. First by Spitzer, which is an infrared satellite. Again, this is done in kind of an imaging mode, broadband kind of imaging. And with a sounding rocket experiment called CYBER at shorter wavelengths. And both of these measurements show there's excess brightness associated with the clustering. In other words, there's more clustering signal than I would have expected from all the galaxies I know about. So what's going on? Well, the answer is really we don't know. One theory that came out was that it's from first stars, but that doesn't seem likely because you'd have to be really, really bright. Or maybe we know this phenomena happens in like this cluster here, where there's stars that are thrown out from their host galaxies. And the glow from those stray stars is pretty bright, actually. And so maybe there could be some process like that that's happening at much more recent times. Well, the best way to sort out these two cases is really we need multi-wavelength information, because all that light piles up, so we can't even distinguish these two extreme cases to really understand what's happening. Okay, so here's the idea. SPHEREx, we want to study the light, but we're not going to do it by studying the individual galaxies. So if we did this with a big telescope, we would find these individual galaxies, assign them redshifts, and this is the information that we would have. Okay. Instead of doing that, we're going to take a blurry image of this structure and just use that information in the image itself as a tracer for the total light production. And that has actually, it's quite different, and it has a number of advantages. One advantage is that we see light from whatever produces it. So if there's like these diffuse fuzzy emission from stray stars or first stars or whatever, we see it. It's kind of democratic. It'll measure the emission no matter what the production is, and that's because these dark matter wells that are huge, okay? If they're dwarf galaxies, for example, really hard to see with the big telescope, again, we'd see it. Even exotic things like dark matter decay, we could potentially see it. But the key is really, how do we break it apart? How do we understand the history? And that's where spectroscopy comes in. We have actually 96 pictures of this projection. And so then the idea is we can tease it apart and understand the history, how much came from, what emission mechanism. So that's what SPHEREx will contribute to this. And then finally, our last theme, what are the conditions for life outside the solar system? We only have one data point for this field, and that's life in our own solar system. Well, actually, life on Earth. And, well, what do we know about life on Earth? It seems to be really closely associated with liquid water. If you go to the South Pole, there isn't very much life on the polar plateau where all the water's in the form of ices. It's really associated with liquid water. Well, how did that liquid water get to the Earth? We don't think it came from the Earth. It looks like it had an interstellar origin. And the process that this happened by is a matter of some debate. Maybe it was delivered in the early solar system by comets or asteroids. We know both of these have water. Perhaps they came from something called the Kuiper Belt, which is around the orbit of Pluto, possibly further out. Well, where did those come from? It turns out that if you want to understand how water exists in the interstellar medium where stars are going to form, almost all that water is actually in the form of ice, not water vapor. Something like 99.9% of the water in dense molecular clouds is actually in interstellar ices. What that means is there are these things called dust grains, and they have mantles where interstellar chemistry happens slowly but freezes compounds like water on the surface of the dust grains. And it's not just water. There's other materials as well, such as carbon monoxide, carbon dioxide, or methanol. You might recognize these as being important ingredients for organic chemistry. So this role of ices is thought to be pretty important. And that parent cloud of ices eventually, as the young stars form, somehow got into the inner solar system, and we think has a deep connection with life on Earth. The role of interstellar ices turn out have not been particularly well studied. There's a couple hundred spectra of ices, and what SPHEREx is going to do is it's going to measure the whole sky and look for abundances of interstellar ices. Water, in particular, that's this big absorption feature out here, is really, obviously of great interest. But there are other species, as I mentioned, carbon dioxide, carbon monoxide, methanol, isotopes of carbon dioxide. And by doing this survey over the whole sky, we're going to measure the abundance of ices in something like 1 million sources. And it's going to go from the conditions in stellar nurseries. Basically, before stars form, this ice is present in the interstellar medium. We use a star here as like a background light, and we can determine from spectroscopy the abundance of ices. This is actually a measured spectrum. So if we look at the absorption, these bands here, it's the background light of the star, but it's getting absorbed by the foreground ice features. And then as time goes on, you start to form young stellar envelopes. We can do the same thing, see if the composition of ices changes or evolves to disk systems, which are now starting to form the protoplanetary disk around the young star. And we know of even some systems that are going through basically the analog of what we think happened in our own solar system, this period of what's called the late bombardment, where all these interstellar bodies apparently came into the inner solar system. We know of cases like that, and we can study those as well, which would be really interesting. And just the number and abundance here is really fantastic. We're predicting, as I said, about 1 million solid detections of ice features, most of them in the plane of our galaxy. Okay, so finally, the last part of SPHEREx is we're measuring the whole sky. And so as a consequence, there's going to be an enormous data set, the first of its kind, doing spectroscopy everywhere on the celestial sphere. And that data set's going to be very rich. We'll have a huge number of galaxies, hundreds of millions with reliable spectra. The statistical power of all those galaxies in studying them is going to be new and powerful. For stars, there'll be spectra of main sequence stars, again, something like 100 million of them. But many of these are going to be interesting cases. Young low mass stars called brown dwarfs, which are just on the edge of nuclear fusion, stars that are forming dust, and some cataclysmic events. It'll be interesting things also in terms of, for example, quasars. Quasars are galaxies where a black hole is at the center and it's active. We don't know how far out quasars go. We know they go out to early times, out to a redshift of 7 now. There's a couple of examples going out that far in cosmic time. Are there more? We don't know. but they're going to pop right out of the SPHEREx data set. We can also measure comets and asteroids in our own solar system and do unique things like measuring line emission in our galaxy. So it's going to be incredibly interesting, and I think there'll be a cottage industry. Well, I know this from past experience. Astronomers are going to go through the data and find stuff that we hadn't thought of. There's a strong tradition in doing just that, going back to the first infrared all-sky survey, IRAS, which is a Caltech JPL mission from when I was in high school. And IRAS is still actively used by astronomers. It's already got almost 1 million citations in the scientific literature, and it just keeps going. There are more like this. GALAX mission, for example, also from Caltech, TUMAS, and so forth. And the same things happen. Astronomers use these, and SPHEREx will fall into this grand tradition. Since we didn't know what astronomers were going to do with our data, we invited them to come on down. One of them was at Caltech at the KISS Center, Keck Center, and one was out here at Harvard in February. So you knew people must be determined. And we asked, not to give your usual lecture, but just to think about what you do with the data. What can we provide to assist you in that process? And as you might expect, came up with a whole list of things we hadn't thought of. And so we now have we've summarized this experience in a couple of papers. And it's a long list, but just to give you a couple of examples, SPHEREx will help us understand the properties of planets going around neighboring stars. Okay, these are called exoplanets. And it turns out if you want to understand the mass and the radius of exoplanets, well, one of the big uncertainties is actually just the property of the star that's going around. And so SPHEREx is going to measure the spectra of all those stars in the process of doing the whole sky. And it turns out this tightens up the errors on the properties of exoplanets. It's a great idea. Again, something that just comes out of SPHEREx, and we hadn't even thought of it. I expect this discovery process will continue, and I look forward to seeing more things that we hadn't thought of as the data come out. Okay, so just to summarize, this is our team. It is a very rare event because everyone's dressed up. That was from our site visit. Never going to happen again. But you can see we're really excited. This is the announcement of SPHEREx being selected, and we're really looking forward to now rolling up our sleeves and getting to work and building this thing. And thanks for your attention.